So just hand those in, slide them all down here, bring them to the center. I'll come grab them.
So sir, just to make sure,
Yeah.
I'm not allowed to use the TI Inspire 2 because it has the cast.
Which one? Oh, it does have the cast?
So those aren't allowed in the class, right?
Well, on our next test, right? I mean, technically, no. Do you have another one or no?
I mean, I have the TI 84.
Yeah, use that then.
I never
Yeah.
use this calculator. I don't like it.
Yeah. Yeah, only because the cast can do all of this, basically, you know? So, all right. Anybody else? Anybody else? How was it? I mean, yeah? Interesting? I was hoping it would be worth your time, that you would learn something from it, right? That's the whole plan. Anybody else? Quiz from last time. I asked you to bring your calculators today, right? So hopefully you remember. Did anybody check one out? You did? Was it easy?
No, yeah, you just.
Yeah.
Honestly, they didn't even ask for my student ID.
Oh, good.
They literally just asked me to show any ID.
Oh, okay, good.
It's like you fill out a little thing and it takes like a minute, and then you just wait for an email. You got one back in the same day.
Very good.
Got it the next day.
Good, good. Well, thank you for doing that. All right, so what we're going to do here to start class is we're going to start by working with the calculators, all right? So in our formula sheets, okay, we have, yes, we have this. I'm going to put it on the, come on, man. What's going on? Okay, that thing doesn't want to go away. In our formula sheets, we have this document here, solving systems of equations using the RREF feature on your calculator. And I cannot get that damn thing to move out of the way. Why is that not moving? Oh, there, I can do that. So look, let me preface this with the following statement. I realize that there are different ways to solve systems of equations using your calculators, all right? And some of you are very familiar with how to do it, all right, on your calculator. And I'm not here to reteach you if you already know how to do it. What I'm going to show you here may look more tedious than what you know, but this works for all the different TI model calculators. So I'm trying to give you something that's more universal, all right? So what we're going to do is we're going to try and solve that system of equations right up there, 3x plus y plus z equals 4. If you came in late, make sure you turn in your quiz. Just put it on the corner of my desk. 2x minus 4y minus 2z equals 2, and then x minus y minus z equals 0. All right, so we're trying to solve this equation. Now going back, this is college algebra. Sorry, solve this system of equations. This is college algebra. What we're trying to do is figure out, is there a value of x, y, and z, three things, right? X, y, and z that make this equation true, and this equation true simultaneously, right? And so, again, going back to your college algebra experience, what you would do now is you would solve it by using probably something called elimination. I'm going to use a different sort of method here. I'm going to convert this into what we call an augmented matrix. And we don't need to get into the theory of this, okay? Just understand all I'm doing is making sure, first of all, that all my x's are lined up, y's are lined up, z's are lined up, equals, and then number. And once I do that, all I'm going to do is just write down what all the coefficients are, just the numbers. So I create this thing called an augmented matrix, which is the numbers 3, 1, 1 right there, and then positive 4, and then 2, negative 4, negative 2, 2, and then 1, negative 1, negative 1, 0. Right, this is called an augmented matrix. And all it does, it just makes our life easier because we have less letters in there, right? And we can use our elimination method just using these coefficients. But our calculator will do that for us. And so what we need to do is put this matrix into our calculator at this point. And what our calculator is going to do is it's going to return to us a new matrix, and it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1, and then there's going to be a number here, and a number here. Okay, so the calculator is going to do this step for us. And we're going to be using this thing called RREF to do this, and I'll tell you what that stands for in a second. But think about what this represents. Think about what this means. Right? This 3 was the number in front of x, right? This 1 was the number in front of y, this number here was in front of z, and then this was the number on the other side of the equation. So what would this first line really mean if we converted it back with x, y's, and z's? It would be the value of x, wouldn't it be? It would be 1x equals some number, right? And then this one would be what? The y is some number. And then the last one would be z is a number. Do you see that? So this operation in our calculator does this for us and returns back x, y, and z, right? This stands for reduced row echelon form. How many of you are going to take linear algebra? Anyone? Okay, so you'll talk more about this in linear algebra. Reduced row echelon form. We don't need to worry about doing it. We're going to have our calculators do it. So the question is, how do we type that into our calculator to have it do that for us? So this right here is the syntax. You first need to call up on your calculator the RREF function. And to do that, there's really one of two ways on your calculator. You either have a math menu, and within that math menu, you have a matrix menu. And within that matrix menu, you should have RREF or something like that. Or some calculators just have a matrix key. So I want everyone right now to try and find the RREF. No do you have one though?
I have one.
You have one.
Yeah.
Okay. Do you have one? Okay, you just don't have it. Okay. So do you have one? You don't have one? You're going to check one out? Okay. All right. So everyone looking, do you find it? Yeah. Do you have one? You're going to get one?
Yeah.
Okay. Do you have one?
I'm going to check one out.
Check one out. Yeah, check one out. All right. Which kind is that?
The TI-4 plus CE.
Oh, okay. It looks all fancy. I don't know. Yeah. Okay. So did you find RREF?
It's actually dead. But
Oh, it's dead. Okay. Did you find it? Is anybody having trouble finding RREF? You're having trouble? Okay. Once you get it, you can start trying to type this in if you want, but if you want to wait, you can. All right. For yours, hit the, see above the, okay, now go to math and then scroll down. So you might want to keep going. And be careful, there's two of them. There's an REF and there's an RREF. Keep going. I don't know what you hit to get there. Did you hit the math menu? Okay, look below that. See that key above it? It says matrix. So clear that out. Hit the second key, then that one. Okay, then go over to math, and then scroll down. Second matrix, math, and then scroll down. RREF, yep. You get it? Hit enter now, and now it's ready. Okay, so once, anyone else need help getting to RREF? You need help?
So, Matt, and then
No, for yours, see that matrix in blue? So clear out of there. So you'll hit the second key, then matrix, and then you go to math, And now scroll down. And just make sure you do the RREF. Y'all have the same kind, I think. So is everyone good now? So the way that the RREF works is once you have RREF up on your home screen, you now are going to tell it that you're going to give it a matrix, all right? And the syntax has to be perfect here. You can't mess up anything, all right? So this should be sitting on your home screen, right?
Yes.
You have to start with a bracket. And I tell you right there what that bracket means. The first bracket is telling the computer, I'm starting the matrix, all right? Then you have a second bracket. We'll call this an open bracket. And that's telling the computer, okay, here comes my first row of numbers. And then what you're going to do is you're going to type in this row of numbers with commas between each number. And so you have to find your bracket key, you have to find your comma key. So you'll put in 3, comma, 1, comma, 1, comma, 4, close bracket. That closes off the first row. Make sense? No comma, open bracket again. Second row of numbers. 2, comma. When you put in -4, you have to use your negative key, not your minus key, right? There's two different keys on your calculator. One of them is subtraction, the other one is negative. So you put in -4, comma, where are we? -2, comma, 2, close the bracket. Javon, you all right? What are you looking for? The comma. I think it's above the 7? No.
Yeah.
Above the 9?
Above the 7.
Above the 7? Depends on the calculator. Did you find it? Yeah? And the bracket, you got the bracket? I think the bracket's above the plus or minus, right? Or something, no? Every calculator is a little different. Multiplication, yeah. All right, so now bracket again, starting my third row of numbers. 1, comma, -1, comma, -1, comma, 0. Close the bracket. That closes my third row, and I'm done with the rows, right? So now what I need to do is close the bracket again. That closes out the matrix, right? And then I need a parenthesis to close out the function. And now hit enter. And if you get an error, you mess something up, right? But you should get something that is displaying something similar to this. You might have to scroll and move around, but you should see 1, 0, 0, and then what number do you see? 1, and then 0, 1, 0, and then -1, and then 0, 0, 1, 2. And those are your solutions. So the right side of your answer, see that, your right side over there? What answers did we get here? We got 1, -1, 2. This is your x, your y, and your z. So that means that if you plug those values in for x, y, and z, it will solve all of those equations simultaneously. The good thing about this method is that once you start your matrix, you can have as many rows as you want, right? As many as you want. You don't have to just have 3 rows. You could have 5 rows. You could have 7 rows, right? And then close off and then close off. Yes?
So does it only work for linear?
Yes, this is only for linear equations. In fact, when you take linear algebra, that class is all about linear equations, not about nonlinear. So this is a system of linear equations. Systems of nonlinear equations are extremely difficult to solve in general. We don't have a nice like Gaussian elimination method for it. Good question. All right. We ready to move on? I have another one for you. Let's see if you get this one. This is the problem that we're going to end class with. So let's go ahead and just solve the matrix now. All right. The matrix that we're going to have a little bit later today is going to be, we're going to have A plus C equals 3, -3A plus B plus 6C plus D equals -6. We're going to have -16A minus 6b plus 9c plus 6d equals negative 11. And finally, 6a plus 2b plus 9d equals negative 14. So this is a system of how many equations? 4 equations and 4 unknown variables. 4 linear equations, 4 unknown variables. I don't think anyone here wants to go through Gaussian elimination on this, right? I mean, could we? Yeah, but do we want to? No, absolutely not, right? So this is our equation. Let's get the matrix set up, right? In other words, let's write this part now. So let's see. When I do my matrix, just remember, this is going to be a column for the A's, the B's, the C's, the D's, and then equals, and then this side's the number. That's the format. That's the format for each of these rows of numbers, right? Kind of like what we had here. We had x, y, z equals a number. X, y, z equals a number. X, y, z equals a number. Here we're using A, B, C, and D instead of x, y, z, right? They're still just things we don't know. So what's my first row of numbers? 1, 0, 1, 0, 3. Okay? You've got to have the zeros there, right? Because you've got no B's and no D's. Next equation, negative 3, 1, 6, 1, negative 6. You get the idea here? We're going to have 4 rows. Negative 16, negative 6, 9. What if you mess up one of those numbers? It's over, right? It's over. At that point, it's over. Unless you accidentally mess up again and you get back on the right path somehow. I've seen that happen before. Okay, let's see. 6, 2, what? 0, 9, negative 14. Let me just double check this. Well, I'll know when we get the answer. So now you've got to type that in to the calculator using the RREF. It's not a race here. You want to take your time, get your syntax right. You know, anything you do on your calculator is going to be faster than doing this by hand. Was there a question? No? All right, so I'll put what I would type in here, and then while you're doing it, parenthesis, bracket, bracket. Anyone get it yet?
Yeah.
Are they nice numbers?
Yeah.
They should be. I made the problem nice, so. That's the syntax. When I say syntax, y'all know what I mean, right? That's the keystrokes, the proper notation for the computer. All right, when you do that, you should get something that's giving you 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And then you have your 4 numbers down the side, which are your answers A, B, C, and D. What are they?
2,
Negative 4,
1,
negative 2. So that means A is 2, B is negative 4, C is 1, and D is negative 2. Let's just check the first equation. Is A plus C 3?
Yes.
Yes. Let's check the maybe this one. 6 times 2 would be what? 12 plus 2 times B. B is negative 4, so negative 8. Plus 9 times D, that's negative 18. Is that equal to negative 14? Yeah. Okay. So I'm just checking it works. Good? Any questions? You have the ability in your hand, in that calculator in your hand, you have the ability to theoretically solve a system of n equations with n unknowns. You can do that with your calculator. All right, let's move on now. Can I? Yep. All right. So last time we basically spent the entire class getting ourselves ready for today. We now need to be able to do partial fraction decomposition in order to find the antiderivative of rational functions. So as a reminder, a rational function is just a polynomial divided by a polynomial. And polynomials are, x to the third minus 2x to the, right, just positive integer powers of x, right? A bunch of them added and subtracted together. So we want to be able to find antiderivatives. So the way partial fractions works is this. And I'm not ready to do integrals yet. Let's say that we have something over, and on the bottom we have a bunch of linear factors. So let's say I have x plus 2, x minus 4. This is just reminding you how partial fractions works. Okay, let's say I had 3 distinct linear factors, meaning these are all different, right? These are all linear, and they're all factors, right? And they're different from one another. If I'm going to try and break this up, for each linear factor, I'm going to create a fraction for each linear factor. And above each linear factor, I'm going to put some number, A, B, and C, that I don't know. I don't know what those are, A, B, and C. And then your goal at this point is to find A, B, and C, right? How we do that, well, we'll have to clear fractions and do other things. But what I want you to see with partial fractions for this part is that what do you turn this into? For each distinct linear factor, you do a number, you don't know it, so some letter, over each distinct linear factor, okay? Okay, compare that to this. What if I had something on top and on the bottom I had, how about x plus 2, x minus 4 squared, and then I had x plus 7 cubed. So I have distinct linear factors still, right? But this one is repeated because it's squared. This one is repeated because it's cubed, right? So here's how we do this. For the first distinct linear factor, it's only to the first power, so I'm going to put A over that. Plus, now this one is repeated, right? So what I'm going to do with this one is I'm going to have to write it twice. In other words, I'm going to have to write it like this, x minus 4, without squaring it, put a b on top, and then plus, now, x minus 4 squared, and then put a c on top. Not cx plus d. No. So if you have a linear factor, you just put a letter over it, right? If it's repeated, you have to do a letter over it without squaring it, and then another letter over it, and now you square it. But I'm not done. I have another linear factor, don't I? X plus 7. It's to the third power. So I would do x plus 7. What number here? D, right? Plus, now I have to do x plus 7 squared. What I'm doing is I'm building the power up. And then I have x plus 7 cubed, like that. Yes?
So what did you add?
Well, these might turn out to be negative numbers, so it doesn't matter. I'm just going to say plus, plus. That's just what we do when we do partial fractions. We're somehow taking an expression and ripping it apart into separate terms, right? Terms are separated by addition or subtraction. This could turn out to be a negative 2, in which case that would be minus. Is that okay? Does this make sense? If this had been the 5th power, right, then I would have another one of these, right, which would say plus what? Maybe g over x plus 7 to the 4th, and then Are we running out of letters? E, F, G, H over x plus 7 to the 5th. Got it? All right, now what does that look like in our notes? If you look at our notes for this section, where did that go? Why does that look like that? If you read our notes, it's a little bit harder to interpret that, but that's what this is saying. I know it's hard to see back there, but it's saying if you have some polynomial on top, who cares what it is, and you have a bunch of linear factors on the bottom, you're just going to put a letter over that first linear factor, another letter over the second linear factor, another letter over the third. For each linear factor, you're just going to put a letter on top. Now here we don't use A, B, C, because what if you have 100 linear factors? It's not going to happen here, but what if you did, right? You would run out of letters, right? A, B, C. But if we use subscripts, A sub 1, A sub 2, A sub 3, then we don't run out of letters. All right, the next note says, what if you have a linear factor to a power? Then you have to do a letter over that linear factor to the first power, letter over that linear factor to the second power, letter over that linear factor to the third, and you keep building it up until you get to the kth power. That's what I'm doing there with the x plus 7, the d, the e, the f. You see that? And then the last thing that we need to be able to handle in this class is if you have something like this. If on top you have, who cares, okay? Who cares what's on top? But on the bottom, you have an irreducible quadratic, a non-factorable quadratic, right? So something irreducible would be x squared plus x minus 1. That's a quadratic that you cannot factor, right? So because that can't factor, what do? Well, according to the notes, what we'll do is we will write that quadratic factor that can't be reduced, and on top we will put ax plus b. ax plus b. That's the method, okay? For linear factors, you always put just a or b or c or d or e or f. But for quadratic factors that cannot be factored, right, irreducible ones, you put a linear on top. Why do you think we do that? From last class, we know how to do that, don't we? From last class, we learned how to do this. We know how to do linear over irreducible quadratic from last class, right? So we should be able to handle this. All right, so that would be it. What about this? What if I had that irreducible quadratic to the third power? What do you think I'd have to do? Go ahead. Go ahead.
Yeah, we were going to probably want to do the similar thing of like the kind of the repeated factors.
Exactly.
Until you get to the third power.
Until we get to the third power. And on top of each one, we need it to be linear. So it's going to suck. It'll look like this. ax plus b over the first irreducible quadratic, right, without raising it to a power. That's a b. Plus, now I need another linear on top, linear expression. Cx plus d over x squared plus x minus 1, but this time squared. And then finally, e x plus f, x squared plus x minus 1 to the third. That's as far as we go in this class, is an irreducible quadratic to the third power. I'm sorry. An irreducible quadratic to a power. That's as far as we go. But just if you think about what partial fractions really is, what if we had a cubic down here, something with x cubed that we couldn't break down? What do you think we would put on top? A quadratic. So when we came over here, it'd be quadratic on top. Do y'all see that everything we've done, the numerator, the a, is 1 degree less than what's down here, at least what our factor was. This is a linear factor. That's a constant, linear constant. So here, quadratic, linear, quadratic, linear. So if we had cubic on the bottom, we would want quadratic on the top. If we had 4th degree on the bottom, we would want 3rd degree on top, and so on and so forth. We are stopping at quadratic though, all right? All right. Now this just tells you what we do, right? Like it tells you what our goal is to try and figure out what these letters are. It doesn't show you how to do it though, right? This is just so we know how to break it down. So let's start getting into the actual examples. And let's put up the actual steps for partial fraction decomposition. So the steps are right here. If we have a rational function, okay, so if we're looking at a rational function, which is the ratio of two polynomial functions, these are all examples of rational functions here. If we have one of those, the strategy for finding the antiderivative is this. First, we inspect the degree of the numerator and the denominator. What's the degree?
The degree is the
Highest power. So we look at the numerator, we look at the highest power of x. We look at the denominator, look at the highest power of x. If the degree of the numerator, can you all read this? I'll make it a little bigger. I'm doing this wireless projection now, so it's a little laggy here. If the degree of the numerator is less than the degree of the denominator, that means the degree on the bottom is bigger than the top, you will move on to the next step. But if the degree of the numerator is bigger than or equal to the denominator, you're first going to have to do long division. All right? So, and then once we do that, we will start breaking everything down using what I just showed you on the board. So let's just get right into it. Let's do this first one. So we would like to find the antiderivative of x cubed plus x over x minus 1. Yeah, so we're gonna see first that we are dealing with a rational function. We're also going to rule out everything else we know, right? Is this power rule? Is this basic U sub? Is this integration by parts? Is this a trigonometric substitution? Right? We've got, remember I said Rolodex? I told my wife about that. She laughed at me because she's like, nobody knows what a freaking Rolodex is, right? So we have to make sure that this can't be done easily any other way, right? We don't want to waste our time doing partial fractions if we can do it with a basic U sub or something. Now this doesn't go easily. So we are going to go here. And we're going to say, all right, look at the degree of the numerator, 3. Degree of the denominator is 1. I need long division because this, if this is bigger than or equal to this, then I've got to have long division. So now, long division, over here, I'll do it. So long division, it's been a long time, right?